everyone doing today?
Good.
All right. I've been told it's supposed to be pretty stormy for a little while, so just be careful and all that. Stay dry, stay warm. Any questions before we get started? All right. So today is Wednesday, March 23rd. Wanted to say that number wrong. And normal week for us, lab as usual. We're covering pressure, buoyant force. I'm going to be really combining chapters 5 and 6 together because they're really just extensions of one another. So during this week, we'll be finishing chapter 5 and segueing immediately into chapter 6. In fact, the chapter 5 homework will kind of be chapter 5 and 6 combined, really, because they're just so interconnected. It's kind of hard to find questions from one that don't necessarily involve the other. So for that reason, we're going to end chapter 5 this week, start chapter 6 this week, and that'll continue a little bit into next week. I'm going to be pushing back the chapter 5 homework that's currently due on the 28th, since it has some chapter 6 stuff in it anyway by accident. That'll be due at the earliest Friday the 1st. Chapter 6 will be pretty quick because it's really just more fluid pressure stuff, and then we'll move on to heat and thermodynamics, which will take up chapters 7 and 8. How do you feel so far? All right. Well, picking up where we left off, we've been examining the concept of buoyancy. We've covered the formula. I don't know why that's supposed to be the view on my screen. Something's backwards. It did that last time, and I don't know why. Button 40 that I didn't know existed. How many times in your academic career has a class been delayed because a teacher didn't understand their own technology? I know it happened to me in school. All right, so we left off looking at the buoyant force formula. We talked a bit about its in and outs. Buoyant force, the force that will cause an object to float in the fluid, is equal to the density of the fluid you are submerged in times the volume of the submerged object times the acceleration due to gravity of the planet you're on. We've talked a bit about this formula, but we get to actually use it much in an example. So, the reason I wrote it on the board is I'm now going to change slides and we are going to use it in an example. The purpose of a submarine is basically to take that buoyant force formula and create a vehicle that's able to control the buoyant force acting on it. If the submarine is floating on top of the water, then it has increased the buoyant force to such an extreme that water's literally trying to push the sub out of itself. But submarines have, at least older submarines, I don't entirely know the modern technology, but at least older submarines would sink by letting water into storage tanks that are contained on the sides of them. Normally those tanks are filled with air, so the submarine is lighter when there's air in them. But if the tanks are filled with water, then it's just heavier. The sub's volume is the same, but now it just weighs more, and so it sinks. I guess really the buoyant force doesn't change, the force of gravity does. Yes.
Never mind.
So we have here a submarine. We don't actually know how big it is. We'll get to that part later. What we do know is it is floating in seawater. And seawater is technically more dense than fresh water. There's more stuff dissolved in it. There's some extra mass because of the salt. So we know the density of what we are floating in, and the first thing we are asked is, this submarine, going to have a mass of 43,000 kilograms, is floating on the water's surface. Part of the submarine is sticking out of the water, kind of like the old scene where the periscope comes out of the top. So we're close enough to the water's surface that some of the submarine is exposed. First question, if that's the sub's mass, what is the force of buoyancy currently acting on the submarine? Now, do we actually have enough information to use this formula to find that answer right now? We do not. We want buoyant force. We know the density of what we're floating in. We also know, we can assume we're on planet Earth, so we use 9.81 here. But we don't know the volume of the submarine yet. We have just no concept of that. Instead, we know the sub's mass. So this formula actually is not what we want to use at first. So instead, I will draw your attention to something that I mentioned, but now I want to make sure is ingrained in your minds and your notes. In order to float, gravity and buoyant force have to add up to zero. The buoyant force has to be strong enough to overcome gravity. So if we look at all the forces currently acting on this submarine, its own weight pulls down, buoyant force pulls up, and they have to add up to zero, which means they must be equal and opposite. For the sub to float, this has to be true. If the two forces were different, it would begin rising or falling. So to maintain a consistent depth, this has to be true, the two have to be equal. So we can kind of find the buoyant force by determining the weight of the object. How does that feel so far? Okay, so again, main thing to remember, if something is floating, force of gravity and buoyant force must be equal. It's not accelerating up or down. So, simplify this a little bit. Two forces must be equal and opposite. Buoyant force will equal the weight of the sub, which will be its mass, 43,000 kilograms times negative 9.81. Your negative signs might be a little bit tricky here. Gravity does point down and the buoyant force points up. So we kind of end up canceling the negative inherent to 9.8 due to the, if we look at this original version I wrote here, force of gravity plus buoyant force equals 0. Therefore, buoyant force equals negative force of gravity. But force of gravity is a negative number, so the buoyant force becomes a positive number because it lifts the sub upwards. How does that feel? Yes?
Can you say that again?
Yes, I can. The two forces, gravity points down, buoyant force points up, they must oppose each other. So one of them has to be negative, one of them has to be positive. Therefore, as long as they're the same number, they should add up to 0. We don't know the numbers yet, so if we just take this formula and say we're solving for buoyant force, we're going to subtract force of gravity to the other side, that will technically become buoyant force equals negative force of gravity. But force of gravity is a negative number because it points down. So negative times negative gives us our positive buoyant force, which we would expect because it would need to point upwards. Did that help at all? Okay. If at any point anyone needs me to repeat anything or say it differently, let me know. Everyone learns differently and that's okay. Ultimately, the number for the weight should also be the number for buoyant force. And that's going to be a lot of force because there's a lot of mass in the sub and that number is just going to get bigger as we calculate weight from it. So, buoyant force will be equal to my faith in my own mental math skills is failing me. It's at least 400,000. Anyone's math differ with 421,830 newtons? All right. So that is a lot of force, but it takes a lot of force in order to lift a giant vessel made out of metal and keep it floating on the surface. The same is true for boats. And now we know the buoyant force. So our next question is, only 1/5 of this submarine is exposed when it is floating. So as it's floating on the surface, most of it is still under the water. Only enough of it is on the surface for the periscope to come out and maybe for some people to come out on a small deck, because some subs do have decks. And we know that, I'll draw a quick picture. So this is our submersible potato, I guess. Most of it's still underwater. Only part of it is above the water. Specifically, 1/5 of it is above the water. So, first question, what is the volume of submarine that is under the water? Now, the portion under the water is important because that's the portion that determines the buoyant force. However much sub is underwater is the amount of sub that is pushing water out of the way. Therefore, that's the amount of the object that buoyant force cares about. So the V in the buoyant force formula is the volume under the water. So if we solve for this V, that is the submerged portion of the submarine. The submerged 4/5 of it. We now know buoyant force, we know water density, we know 9.81, so we can now use this formula to find that submerged volume, the 4/5 that is under the water. So, found buoyant force a minute ago, very large number, equal to density of salt water, which is 1,025. Fresh water is just 1,000 kilograms per meter cubed, excuse me. Times volume, that's what we're going to be solving for, and again, times 9.81. So our V submerged is the last term. arrive at. Yes.
Couldn't you have done that at the beginning if you used like the density formula? Cause I had that number earlier, but you did it that way, so I didn't know if there was like a certain way to do it.
Yeah, like
Cause when we were looking for the, force of buoyancy, I used the D equals M over V,
And so
and that's how I got the volume.
Yeah.
And I just plugged it back into the equation.
Force of buoyancy.
Yes, you could. That's very, very good thinking. Yes, density of salt water equals mass of the submarine divided by the volume of the submarine. Yes, that would work. Now, officially, let me start by saying you're absolutely correct. That will work. You're right. The reason that works is this is the density of salt water, so technically this should be the mass of salt water divided by the volume of salt water. But the volume of salt water pushed out of the way by the submarine is the same as the submerged portion of the submarine. 1 meter cubed of space of 1 meter cubed of object will push 1 meter cubed of water out of the way. So those would end up being the same number. M would therefore be the mass of that salt water, but that would also have to be the same mass as the submarine that it's making float. Because the mass of water pushed out of the way is equal to the mass that it can support in itself. So, same number, and you're correct. So that does absolutely work. So that intermediary step wasn't all that important, actually. I feel a little bit silly, and you should feel very smart. So that absolutely works. That is basically what we've done here. Because this formula, we kind of just divided the 9.8 that we put in there out anyway. And then it's just, you're correct, ultimately. We're going to get the same number here regardless. So, what is that submerged portion? What is the submerged volume?
I just wrote out the whole
Yeah, if I'm not manually tracking sig figs, I'll tend to round to the hundredths place. But you're right, it rounds up to about 42 meters cubed is the unit of volume we're using right now. Which is actually a lot. 42 is not a very large number, but a meter cubed is a lot of space, because that's a meter times a meter times a meter. So, very big submarine actually, and that's just the part of it under the water. If 1/5 of it is above the water, my last question to you, and this is more a geometry question, what is the submarine's total volume if that's the amount of it under the water? This one's less physics and more of a geometry puzzle.
Would it be 209.75?
It would not be 209, but that multiplied by 5, I can see where that comes from. You're on the right track. Again, this is more of a puzzle than a formula-based question, so I'm going to show you my logic for it. We're told that 1/5 of the submarine is above the water as we're floating right now, which means that 4/5 is under the water. This portion is 4/5 of the total volume. So, that V submerged portion is equal to 4/5 the total volume. And we can kind of use this statement as a formula. Submerged portion is equal to 4/5 of the total, therefore, if we multiply what we just found for V submerged by 5/4, that would give us V total back. Any issues with jumping from one of this first line to the second one? Suppose I should have shown that one at a time. Now let me backtrack a little. V submerged equals 4/5 V total. Any questions with this line? All right. If we want V total by itself, we can start by multiplying both sides by 5, which would give us 5 times V submerged equals 4 times V total. Then divide both sides by 4. Five-fourths V submerged is V total. Yes?
Somehow that just confused me more than I was initially.
Oh, sorry. Okay. And do you have any issues with this statement?
No.
Okay. V submerged equals 4/5 V total. We want V total by itself. So it's got 4/5 multiplied by it. We want to cancel out those two terms and send them to the other side. And this number, 5 is in the denominator. So to cancel it out, we would multiply both sides by 5. Multiply this side by 5. The denominator 5 cancels out, which would put a 5 in the numerator on the other side.
Okay, yeah. I just didn't register in my head. I get it now.
All right. And ultimately, I think the final answer is about 52.4, which fits the scale of what we've been told. If about 42 is under the water and that's 4/5, we would expect the total to not be that much bigger. It would be 1/5 bigger than just the part under the water. So, how's this one feel? Okay. Any questions as we finish this one or about buoyancy? Okay. In a minute, we're going to switch gears, move from buoyancy onto the next individual concept, but I'm actually going to call a quick pause. We're about halfway through the lecture, and I want to take a second to add in one more quick slide to these notes. So if you guys need a minute to maybe go to the restroom or get some water, now's a good time. In a minute, once I've edited the notes a little bit, we'll reconvene, talk a little bit more about buoyancy, and then move on to the next part of pressure. So just one sec.
Can I move you back a bit?
Oh. What are you looking for?
It's like a small silver ball that's connected to my piercing. I can't find it.
Shit, Georgia down. Nobody come out there. They want to know
Alright, any needs or questions from anybody? Okay, so, a couple small buoyancy concept, but why did it do that again? It knows that this is the second screen. Alright, so, couple rapid fire buoyancy questions before we move on to Pascal's principle. One, why would a helium balloon float in air? What's the easiest explanation for why helium would float in air? Correct. Also correct. So helium is just less dense than air. If you've taken many chemistry classes and looked at the periodic table, helium is element number 2, which means it's the second lightest element that exists. The only other lighter one is hydrogen. Air, which is mostly made out of nitrogen and oxygen, is at times anywhere but at least 20 times more dense. So helium is less dense than air, therefore it floats in air. But at a certain point, a balloon will rise high enough into the atmosphere where the air density drops and the balloon freezes and then it pops. But in general, helium lighter than air. Hydrogen is also lighter than air, so you can make hydrogen balloons float. However, hydrogen can explode, so I wouldn't recommend it. Helium doesn't explode, that's why we use that one in parties. Also, the reason helium, if you inhale it, makes your voice higher pitched is because the helium literally floats up out of your lungs. Like, you can't keep it down. As long as your mouth and nose are open, the helium will just literally force its way out by just rising back up through your esophagus and out of your breathing orifices. And as it rises, it literally pushes upwards on your vocal cords, literally setting you upwards an octave. There's a few gases heavier than air that do the opposite and make your voice deeper when you breathe them. But they sit in your lungs, so I wouldn't recommend it. Next, one more quick buoyancy formula question. Humans have the potential to float in water. Fresh water has a density of 1,000 kilograms per meter cubed, and if a specific human that is able to float floats with 0.9 meters cubed of their volume under the water, so let's say that their head is above the water, 0.9 of them is under the water, what is the buoyant force currently acting on them? Fluid density times submerged volume times 9.8. We'll give you your number. And lastly, salt water is more dense than fresh water. I mentioned that a second ago. There's just literally more stuff in it per unit volume because there's salt dissolved in it, and if it's ocean water, there's other trace elements besides salt as well. So, salt water, seawater, more dense than fresh water. For a human, assuming your density is constant, does that make it easier to float in seawater or harder to float in seawater?
Easier.
Easier. If the fluid is more dense, that would create more buoyant force. So it would be easier for a human to float in salt water. The, I think, easiest body of water for a human to float in on Earth is the Dead Sea, which is the saltiest water naturally occurring on the planet. It's the most dense portion of water that I know of on Earth. So if you ever go to the Dead Sea, or frankly even Salt Lake, there's just so much salt, the density is so high, it creates a ridiculous amount of buoyant force, you'll float very easily. The downside is it's so thick with salt that it feels like mud, so it's a very weird experience. So, we're going to move on now from buoyancy to the next fluid pressure related concept, and don't have much longer today, so we'll just introduce the concept and I'll show you some applications of it. We'll work some examples next time. While you're reading over this information, I do have a lead-in question to ask you. Who here is familiar with hydraulic systems, say in cars or possibly in large machines? Okay. When I refer to, say, hydraulics in cars, usually those are used for a car to be able to, on command, raise or lower part of itself. You just throw a switch and the back top, the back end rises itself, maybe to help with an incline or to show off. Those hydraulic systems, and frankly a lot of various moving machines dating back to the Industrial Revolution, specifically accomplish those feats, not with, say, mechanization, like with robot parts or, electricity, but rather with hydraulics, which is to say by pushing fluid through pipes and those fluids exerting forces to make certain things happen. Specifically liquid fluids, because gases, if you push on them, can be compressed. That's why certain gas tanks are able to hold a lot of gas in them. You're literally able to compress a large amount of gas into a smaller volume because gas is a fluid that can be compressed. But liquids don't actually like being compressed. If you push inwards on water, for example, it tends to fight you on that. Water tends to occupy a specific finite volume. If you were to take a water balloon in your hands and literally just squeeze inward on it, it wouldn't shrink like, say, an air balloon could. It would eventually just pop because as you're pushing in on the water, its volume doesn't change. It wants to escape and take up the same amount of space, so it'll just burst the balloon. Whereas an air balloon can shrink if you squeeze it correctly. Water and liquids don't compress. And that's why, over the years, humans have been able to use them in various hydraulic systems. The reason for this is Pascal's principle. Pascal is a term that's come up a few times as we've studied fluids and pressure. Specifically, the unit Pascals, the unit for pressure. The man Pascal was just a scientist who did a lot of research into this subject. So, most specifically liquid fluids can be approximated as incompressible. Therefore, if you were to push on one part of a fluid, if you say push some amount of water out of the way with your hand, like you just literally, like say you're in the pool and you just dunk your hand under the water. You have pushed on water as you do that. And so your hand has pushed that water out of the way. That water needs to go somewhere else. It needs to occupy some other region of space. Water doesn't compress like air does. Pushing down on the water doesn't make the water smaller, it just makes the water move away. So as you push down on that water with some amount of force, the volume of water that you've now forced away goes somewhere else. And it's technically possible if you were in the right pool or the right tank, as you put your arm under the water, you could see, say, the water level rising. It's the same as when you just enter the bathtub. If your body is in there, then you are taking up space the water used to take up, and the water level rises. It's not that there's more water, it's just that there's now more stuff in the tank, and you are part of that stuff. So if you push on water, that water has to go somewhere, and since you are pushing on the water, as the water tries to escape, it will push back. As you push on water, it will push on you, but as that water moves out of the way and tries to go somewhere else, it will exert force on whatever it encounters along its way to try to move on to the next position and take up the same amount of volume. I'm actually going to swap slides real quick. I'm going to show you the picture for a future sample question. We're not going to do the map yet, I just want to show you the picture. This is an example of one of the most commonly used hydraulic systems still today. This is something that you might see if you were looking behind the scenes at a car auto body shop. You bring your car there, and for several different procedures, they will raise your car up into the air so people can work on the bits on the underside. In order to do that, you have to literally lift the car upwards, which is itself a pretty dangerous task. It takes a large amount of force, and you need a machine that's capable of just holding it there in place. And specifically, if that shop uses a hydraulic system to do this, there's a couple of ways you could do it, but we're going to focus on the hydraulic method for right now. That car will be parked on a lift on some platform. Under that platform is a reservoir of liquid. It's probably not water, but let's just treat it like water for right now. This piston that the car is sitting on is one solid object. It's like a piston. It's, I guess if you're not familiar with that term, it's just a solid piece of metal that's literally sitting on the water. It's trying to float on the water's surface. And so the water beneath it is pushing up on it, because if the piston pushes on the water will push on the piston. There's a certain finite amount of water down here, so there's a certain number of gallons, that number doesn't change. If you want to raise the car up in the air, the point of this system is if you're able to raise the water upwards, the water will push upwards on this piston, and the piston will push up on the car, and the whole thing will rise. So what they do is, there's a second part of the machine, there's a second access to this reservoir, where there's a second piston that either a person or a machine is able to press down on. If you were to exert force on this piece of metal that's able to slide up and down this tube, if you push down on this, you're going to push down on the water's surface. You're going to try to push the water physically downwards. If you push on the water is trying to escape. It needs to go somewhere. You can't really make the water smaller by compressing it, so if you push 1 gallon of water out of the way here, that gallon has to go somewhere else in the reservoir. So you exert force literally on the water itself here. As you push on the water is pushed all the way through the pipe to the other side of the reservoir. And so the force you exert is basically sent from this side to the other. If I push with 1 Newton down on this side, now the water I'm pushing out of the way goes to the other side, and in an attempt to, not really expand, but in an attempt to move, in an attempt to not be compressed, it's going to push up on the other side in a manner similar to Newton's third law. So effectively, you're able to carry force from one side to the other. You're able to take downward force that a machine could pretty regularly generate and convert it into upward force to lift up your car. And any hydraulic system, the word hydraulic just means you have water moving through pipes, pushing on things to accomplish tasks like this, has a fluid reservoir that is moving back and forth as forces are exerted on it to itself push on things and cause various things to happen. In the case of a car with a hydraulic system, it would have fluid moving through its pipes to exert a force, say, upwards on the back axle to lift that half of the car upwards. And then if you wanted to lower it again, the fluid would move away from the back of the car and the force would decrease. So, the term hydraulic refers to this type of a system. This type of a system uses Pascal's principle, the idea that if you exert force on the surface area of a fluid, that fluid will basically continue pushing, like that force will carry through the fluid to the other side of the reservoir. And it will then exert force on the area of the piston over there. If you look here, this piston would have a certain surface area. If I push down on that surface area of the water, that water will then exert a force on the surface area of the other piston. Pascal's principle is simply a ratio of the force to area of the two sides of the reservoir. And we'll look a little bit more at the math for that next time. Last thing I'll point out is there's another word for a system similar to this, and that is pneumatic. If you've heard the term pneumatic before, it's got the silent P on the front, P-N-E-U-matic. That refers to basically the same thing. It just uses gas instead of liquid. So hydraulics, hydro uses liquids, pneumatic, pneumo, pressure uses air or other gas. And we'll do the math for how this works next time. Any questions before we break? All right, we'll reconvene Friday to continue on to chapters 5 and 6. If you're working on the homework, it won't be due Monday, but work on it anyway. And if I don't see you in the lab today, have a nice day. Actually, have a nice day regardless.